Hello and welcome. My name is Hadhemi. I'm a master research student at Polytechnique Montreal, and today I'm going to present an empirical study of the descent of deep learning code. The purpose of this presentation is to study the prevalence, evolution, and bug provenance of code smells in deep learning code. So what I'm going to talk about, the popularity of deep learning applications and some examples, how software engineering is important for this type of application. I'm going to cover the study methodology and research questions. First, we focus on the comparison between code smells in traditional versus deep learning code. Second, we study the trend of code smells over multiple releases. And finally, we tackle the relationship between code smells and bugs. The rise of powerful open source deep learning libraries has contributed to the democratization of deep learning technology. Actually, we notice nowadays a wide adoption of this new technology in several applications, such as search engine, face detection, and autonomous cars. However, maintaining these complex systems over time can be more difficult and more expensive than traditional ones, because they may contain not only all the maintenance issues of traditional software projects, but also additional deep learning specific issues arise from their statistical and data-driven nature. In a prior research work, the authors mentioned the lack of software engineering practices for deep learning systems, and how deep learning practitioners give too much importance to the accuracy of model performance. So I think that the main lessons falls under their code. Just because there is machine learning involved, it doesn't mean you can forget good software engineering practices. Motivated by those results based on Google developers' experience, recent research works investigated the quality of deep learning frameworks and the degree of software engineering practices adopted by their users. The first one studies the characteristics of deep learning systems bugs, their types, root causes, and effects, through analyzing Stack Overflow posts and popular frameworks issues. And the second research work interviews deep learning practitioners to understand their thoughts about software engineering practices and which practices that have been already tried. As far as we know, nobody studies the deep learning system's quality by mining their software repository. So before processing to methodology and research questions, let's define what is code smell and introduce some type from 10 Python code smells that we focus on in our study. In computer programming, code smell is any symptom in the source code of program that possibly indicates a deeper problem. Code smells do not prevent the program from functioning, but it's kind of best practices violation that may increase the risk of bugs or failures in the future. So it affects the software quality. One example of code smells is long lambda function, which is an anonymous function. I mean a function with no name that is extremely long and complex in terms of condition and parameters. Another type is long ternary conditional expression, which is a ternary conditional expression that is extremely long. We have also complex container comprehension, which is one-line comprehension, list, set, or dictionary that contains a large number of clauses and filter expressions. And long method smell, which is a method or a function that is extremely long. In our study, we investigate three research questions as follows. First one is, does deep learning code smell like the traditional software code? Second, what is the global trend of code smells in deep learning projects over multiple releases? And last one, is there a coexistence between code smells and software bugs in deep learning applications? To perform an empirical investigation on the software quality of deep learning projects, we based our study on a set of projects selected from GitHub, having top number of commits. We choose Python language as filter for the extracted projects because it's the most used language in deep learning application. So we are going to profit from previous studies of detecting code smells in traditional Python program. We use the developed tool PySmell and the catalog of smells. We run PySmell on each project and on each version of each repository. We cannot end without studying the coexistence between code smells and software bugs in deep learning application. Thus, we first separate the bug-fixing commits using their labels and extract the files that were changed to fix the bugs. Then we determine whether these changed files contain code smells in our deep learning applications. We also analyze the time spent for fixing the buggy code to compare the time spent when the file is smelly and when it is not. Now we start with the first research question. Comparing the smell occurrences by project type by performing non-parametric Mann-Whitney test, we obtain a p-value that is greater than 0.05. Although there is no difference between deep learning-based and traditional systems in code smell density, we further extend our comparative analysis by considering both type and size of the systems. When considering project size, we notice that the number of code smells per project increases with the increase in project size for both deep learning and traditional software projects, which is consistent with earlier findings with traditional systems in previous works. However, we found two noticeable differences when considering the size. First one is that small deep learning-based projects contain more code smells than that of small traditional projects. On the contrary, large deep learning projects contain comparatively less smells than that of large traditional software projects. We are going now to study more deeply smell occurrences of specific smell type by project type. For group 1, we found no significant difference with p-value greater than 0.05 between traditional and deep learning projects. With respect to large class smell, long method smell, and long scope chaining, which is a long sequence of objects called, these smells are often a result of poor coding practices by the developers, thus they might be invariant of the type of the subject systems. Second group shows the significant difference between deep learning and non-deep learning application with respect to three smells. First one, complex container comprehension. Using a container comprehension that includes list, set, dictionary, it becomes too complex when it contains multiple for clauses or filter expression. We also observed that the smell long ternary conditional expression also occurred the most when compared to its occurrence in traditional repositories. The ternary conditional expression simply allows to test the condition in a single line, replacing the multi-line if-else, making the code compact, but when it contains long expression or it's written in multi-lines, it will be hard to read and confusing. A reason for the high occurrence of the long ternary conditional expression, this could be due to deep learning developers often use ternary conditional operators either to execute a particular routine or to conditionally assign a particular value to configuration setting. And finally, long lambda function, when a lambda function is overly long, which makes code unreadable and loses its benefits. Deep learning developers often choose lambda functions to carry out data processing by creating anonymous functions at runtime and then by sending them to appropriate deep learning routines as parameters. And for the third group, we found also a significant difference with respect to another four smells. We observed a low occurrence of long base class list and long message chain smells in deep learning projects. This could be due to data scientists don't use the object-oriented programming. And we found also that the occurrence of long parameter list smells and multiply nested container smells in traditional projects are high, comparing them to the ones in deep learning projects. We now move on to second research question results. To show the general trend of smells exhibited by deep learning projects over time, we show the distribution of smells by version of each repository. To perform this analysis, we select repositories that have more than 4 versions. We observe that the overall trend over deep learning repositories show increasing. According to these results, there is a possibility that code smells are associated with system development. In particular, developers seem to have not paid sufficient attention to code smells even after numerous releases of the system. Instead, the code may be suffering code smells further and further during the evolution. It stimulates and values the research of our study. And finally, it's time to move on to the last research question. Now we tackle the coexistence between code smells and software bugs. As a result, we found an overlap of nearly 63% of the bug fixing files with files that contain code smells, and that frequent smells like long ternary conditional expression, complex container comprehension, and long parameter list coexist with software bugs more frequently than the others. To gain further insights on the effort needed to fix the bugs in both smelly and smell-free code, we compare the time spent to fix buggy code containing code smells with the time spent to fix buggy code without code smells. We found that fixing the code with code smells takes significantly longer time than fixing the code without any code smells. Now let's move to the final part of my talk, which is about research application. The first finding was about Python-based deep learning applications truly include the code smells found in traditional Python software with varying levels of prevalence, which imply that deep learning code is still written in traditional programming language, which consequently makes it vulnerable to similar code quality issues, and as a result, the application of software engineering practices becomes mandatory to ensure better code quality in both the short and the long term. Second finding was about the most frequent smells among deep learning projects are complex and long one-line statements, which implies that deep learning developers should be aware of the future risks of these Python syntax hacks. Indeed, one-line Python statements are useful as long as their logics are simple. Otherwise, they should be extracted to separate functions that are readable and maintainable. Third finding, the occurrences of smells tend to increase over deep learning code versions, which highlight the fact that keeping these code smells as they are without further refactoring enhances the odds of introducing more of them to the deep learning application code when novel algorithmic repairs and improvements are added. For instance, the extraction of complex one-line statements as separate functions can make them reusable in different code locations and reduce the risk of adding more and more of them in the future. And the last finding was about the coexistence between bugs and code smells, which imply that deep learning developers should be advised that these poor coding practices adversely affect the code structure and its comprehension, which consequently can increase the risks of making mistakes and introducing bugs in the smelly code components. In conclusion, let me sum up the main points. The goal of our empirical work is to study the prevalence, evolution, and bug provenance of code smells in deep learning code. To that aim, we examine 59 open source deep learning systems and compare the results with other 59 traditional open source systems. We conclude that there is no significant difference in the code smell occurrences between deep learning and traditional ones. We identify three types of smells that occur more frequently: long lambda function, long ternary conditional expression, and complex container comprehension. After that, we focused on the trend of code smells over multiple releases, and we report that the number of code smells increases across releases. And finally, we focused on the relationship between code smells and bugs. We report overlap of nearly 63% of the changes files with files that contain code smells, and that frequent smells coexist with software bugs more frequently than the others. That brings me to the end of my presentation. Thank you for your attention.